So now I will take gate problems which is based on availability and reversibility. So first of all, I am taking the problem which is asked in year 2010. I am writing the problem here. Gate AME 2010 problem. So first I will write the problem. Consider the following two processes. Consider the following two processes. A heat source at 1200 Kelvin loses 2500 kg of heat to a sink at to a sink at 800 Kelvin. B. A heat source at 800 Kelvin loses 2000 kg of heat to a sink at 500 Kelvin. So for solving this problem, means for this problem we have to say which of the statement is true. So I am writing which of the following statement is true. Statements is true. So which of the following statement is true? A. Process 1 is more irreversible. Process 1 is more irreversible than process 2. Second, process 2 is more irreversible than process 1. Similarly, the third option is irreversibility associated in both the processes are equal. Both the processes are equal. And number 4, that is D option, both the processes are reversible. Both the processes are reversible. So let's solve this problem. Means we have to find out whether the processes are reversible or irreversible and which process is more irreversible. So if we find out the change in entropy of the universe for these two processes, then the process which is having high change in entropy for universe will be more irreversible. So I will take process 1. So for process 1, I am finding the del S, that is del S universe. So that is process 1. So del S universe, I can find out we are having two reservoirs. One is at 1200 Kelvin and second one is at 800 Kelvin. So 1200 Kelvin is uses heat. So the entropy change for this heat source will be minus 2500 divided by 1200 plus the sink which is getting heat. So it's positive 2500, temperature is 800. So now we can easily calculate the entropy change for the universe for the process 1. So here we are having 2500 divided by 1200. It will come minus 2.1 plus 2500 divided by 800, it will come 3.125. 3.125. So now 3.125 minus 2.1, it will be 1.025 kilojoule per Kelvin. So that is the solution for the first process. Similarly, for second process, we are having the same equation, del S universe equals to, in the second process, source is at 800 Kelvin and it is losing heat 2000 kilojoule. So minus 2000 divided by 800, the same heat, that is 2000, gained by the sink, which is having a temperature 500 Kelvin. So now del S universe in second process we can calculate it easily. That is 2000 divided by 800, it is coming 2.5 plus 2000 divided by 500, it is coming 4. So 4 minus 2.5, it is coming 1.5 kilojoule per Kelvin. So for entropy change of the universe, for second process is 1.5, for first process is 1.025. So I can write del S universe for process first is greater than, is for second process is greater than del S universe for process 1. So process 2 is more irreversible than process 1. So the correct answer in this problem is B. The process 2 is more irreversible than process 1. Take another gate problem which is asked in gate 2007. So I am writing the problem for gate AME 2007. Which combination of the following statements is correct? Which combination of the following statement is correct? P. A gas cools upon expansion only when Joule-Thomson coefficient Thomson coefficient is positive in the temperature range of expansion. That is P statement. Q statement, for a system undergoing a process its entropy remains constant only when the process is reversible. R statement, the work done by a closed system in an adiabatic process is a point function. Is a point function. The S statement is a liquid expands upon freezing. A liquid expands upon freezing upon freezing when the slope of its fusion curve on when the slope of when the slope of its fusion slope of its fusion slope of its fusion curve on pressure temperature temperature diagram is negative. Diagram is negative. So these are the four statements P, Q, R, S, and we have to find out which combination is correct. So options are A, R and S. Option B, that is P and Q. Option C, that is Q, R and S. Option D, that is P, Q and R. So now if you see the first statement, which is saying the gas cools upon expansion only when its Joule Thomson coefficient is possible, is positive. So we know if the Joule Thomson coefficient is positive means it is in cooling region. So this statement is true. Second statement, that is for a system undergoing a process, the entropy remains constant only when the process is reversible. So we know for the reversible process the entropy will remain constant. So Q is also true. The work done by a closed system in an adiabatic process is a point function. Whatever may be the work done, it is work done for adiabatic or isothermal or some other process. Work done will depend on path. So it is a path function. It is not a point function. So R is false. S. In case of S, a liquid expands upon freezing when the slope of its fusion curve on the pressure temperature diagram is negative. This is also true, and the example for this kind of being P, Q, and S. These three statements are true. So here there is no combination for P, Q, and S. So if you see the second option, that is P option, P and Q. So P and Q both are the true statement. So the option B will be the correct answer. So the correct answer is option B. P and Q are the true statements. Take another problem which is asked in GATE 2005. So I am writing the problem which is asked in GATE 2005. First I will write the problem. Nitrogen at an initial state of 10 bar 1 meter cube and 300 Kelvin is expanded isothermally is expanded isothermally to a final volume of to a final volume of 2 meter cube. The PVT relation is the PVT relation is P plus A by V square into V equals to RT, where A is greater than 0. So the final pressure A will be slightly less than 5 bar, will be slightly less than 5 bar. B option will be slightly more than, will be slightly more than 5 bar. C option will be exactly 5 bar, will be exactly 5 bar, and the fourth option, that is D option, cannot be ascertained in the absence of the value of A. Cannot be ascertained in the absence of value of A. Value of A. Value of A. This problem, so I am giving the solution for this problem. Here they are giving relationship between pressure and volume and temperature. So I am writing the relation P plus A by V square. V equals to RT. So it's a isothermal process. So for isothermal process, I can write P1 plus A V1 square. V1 equals to P2 plus A V2 square V2. So here in the problem it is mentioned that P1 is given, that is 10 bar, V1 is given, that is 1 meter cube, temperature is given here 300 Kelvin. So temperature is mentioned in the problem, that is 300 Kelvin. Final volume V2 it is mentioned here, that is 2 meter cube. So if we plug this value here, P1 I will write 10 plus A, V1 square means 1 square, 1. P2 we have to find out P2 plus A, V2 means 2, 2 square, and V2 is 2. So now we are having 10 plus A equals to P2 plus A by 4 into 2. So now we are having 5 plus A by 2 equals to P2 plus A by 4. So P2 will be 5 plus A by 2 minus A by 4. So P2 will be 5 plus A by 4. So the pressure P2 will be greater than 5. So the answer, final pressure will be slightly greater than 5 bar. So the correct answer is pressure will be slightly greater than 5 bar. So correct answer is B. And another problem which is asked in GATE 2004. So GATE AME 2004. So I am writing the problem here first. A steel billet of 2000 kg mass is to be cooled from 1 to 50 Kelvin to 450 Kelvin. The heat released during this process, the heat released during this process is to be used as a source of energy. The ambient temperature is the ambient temperature is ambient temperature is 303 Kelvin, and the specific heat and the specific heat of steel is zero point 0.5 kilojoule per kg. Find the available energy. Find the available energy of this fillet. So now let's solve the problem. So remember one simple equation, that is Q1 equals to available energy plus unavailable energy. So first of all, I will find Q1. So I am, whatever the data given in the problem, I am writing here. Mass is given 2000 kg. Initial temperature T1 is 1250 Kelvin. Final temperature is given 450 Kelvin. And C, that is specifically given 0.5 kilojoule per kg. And ambient temperature, that is denoted by T naught, 303 Kelvin. So first of all, we can find out the Q1, that is heat released during this process. So heat released, you can say that heat released, because heat released during this process is the source of energy, that is Q1. So we know the formula mc delta T. So for this Q1, m we are having 2000 into zero point 0.5 into del T, that is T2 minus T1. So we can see that is 450 minus 1250. So Q1 equals to 450 minus 1250 into zero point 0.5 into 2000. It is coming in terms of megajoule, we can write in terms of megajoule. I can write, or again we can calculate, because we are having m 2000, c 0.5 we are having, and we are having the temperature difference 450 and 1250. So 450 minus 1250 into zero point 0.5 into 2000. So it is 8 into 10 to the power 5 kilojoule. So I am not taking the sign here, because for this equation we have to put the magnitude only. So now I will calculate the del S, that is entropy change. So the entropy change for this process, we can write mc ln T2 by T1. So here for del S, m we are having 2000, c we are having 0.5, ln T2 we are having 450, and T1 we are having 1250. So now let's calculate this thing. 450 divided by 1250, and if we take the log of this, it will be minus 1.21 into zero point 0.5 into 2000. So it will come 1021.65. So del S will come 1021.65 kilojoule per Kelvin. So again here I am not taking the sign, because you know for this formula there is no need of sign, just we have to put the value. So now for unavailable energy we are having the formula T naught del S. So T naught we are having 303. If we multiply it with 1021.65, so 300 multiplied with 1021.65, so it will come 306495. So it will come 306495. So I will again recalculate this thing, because here in the problem it is mentioning that ambient temperature is 303. So for ambient temperature 303, and we are having del S 1021.65. So it is coming 309, sorry, it is coming 309 just wait, it is coming 309,559.95. So we can write 309,560, that is kilojoule. So it is coming in kilojoule. So now we are having Q1, we are having UE, so we can find out available energy. So available energy will be Q1 minus unavailable energy. So the available energy, so Q1, that is 8 into 10 to the power 5 minus 309,560. So available energy we can easily find out 8 into 10 to the power 5 minus 309,560. So it is coming 490,440 kilojoule. So in terms of megajoule, we have to divide it by 10 to the power 3. It will come 490.44 megajoule. So the available energy for this question will be 490.44 megajoule. Now let's take another problem which is asked in GATE 2003. So I am writing the problem here for GATE 2003. So now I am first writing the problem here, considering the relationship TdS equals to del U plus PdV between the entropy, that is denoted by S, internal energy that is denoted by U, pressure that is denoted by P, temperature that is denoted by T, and volume that is denoted by V. So we have to find out which of the following statement is correct. Which of the following statement is correct? So A, it is applicable only for reversible process. It is applicable only for a reversible process. B, for an irreversible process. TdS is greater than del U plus PdV. C, it is valid only for an ideal gas. D, it is equivalent to first law for a reversible process. It is equivalent to first law for a reversible process. So let's solve this problem. I am giving the solution here. We know the first law of thermodynamics. I am writing the first law of thermodynamics here. So in first law of thermodynamics, we are having del Q equals to del U plus del W. And if we are talking about, that is pressure, displacement work, that is, then we can write del Q equals to del U plus PdV And for reversible process, I can write TdS equals to del Q. So I will get TdS equals to del U plus PD. So such kind of expression is applicable for reversible process, but it's the equivalent of first law. So if you see the two option A, it is applicable only for reversible process, it may be right. But the more appropriate answer we have to choose means it's a first law, and it is this kind of the specific form of first law is applicable for reversible process. So we can say that it is equivalent to first law for reversible process. So correct answer will be D. So let's take another gate problem. I am writing gate problem which is asked in year 2002. First I will write the problem. A positive value of Joule-Thomson coefficient of Joule-Thomson coefficient of a fluid means A option, temperature drops during throttling. Temperature drops during throttling. B option, temperature remains constant. Temperature remains constant during throttling. C option, temperature rises during throttling. D option, none of these. So we have already discussed in the theory the positive value of Joule-Thomson coefficient will lie in cooling region, means the temperature will decrease. If you see the options for decreasing temperature, so only A option is correct, temperature drops during throttling. So the correct answer for this question is A. And another problem which is asked in year 2001. So I am writing the problem here which is asked in year 2001. So get ME 2001. So first I will write the problem. A gas having a negative Joule-Thomson Joule-Thomson coefficient, that is mu is less than 0 when throttled will A option become cooler, B option become warmer, C option remain at the same temperature, D option either be cooler or warmer, depending on the type of gas. Depending on the type of gas. So we have already discussed in the theory, if Joule-Thomson coefficient is positive, it means in cooling region, negative, it means in heating region. So for this question, the answer is very straightforward because Joule-Thomson coefficient is negative, so it will be in heating region. So for throttling, the gas will become warmer. So the correct answer for this problem is B. Now let's take another problem which is asked in GATE 2000. So I am writing the problem here. It is for GATE AME 2000. So I am writing the problem. Availability of a system of a system at any given state at any given state is a property of the system, a property of the system. B, the maximum work obtainable, the maximum work obtainable as the system goes to goes to dead state. C option, the total energy of the system, the total energy of the system. And D option, the maximum useful work, the maximum useful work, useful work obtainable, obtainable as the system goes to dead state. So again, it's a straightforward question. Whenever we are talking about availability of system, then we are interested in maximum useful work. We are not interested in maximum work. Whenever availability will come, we are interested in maximum work. So the correct answer for this problem is D. It's a maximum useful work obtainable as the system goes to dead state. So correct answer is D. In GATE 2000, so I am writing the problem here for GATE AME 2000. I am writing the problem for GATE AME 2000. When an ideal gas with constant specific heat with constant specific heats specific heats is is throttled adiabatically adiabatically with negligible changes with negligible negligible changes in kinetic energy and potential energy potential energy. A, change in enthalpy equals to 0, change in temperature will be 0. B, change in enthalpy is greater than 0, change in temperature will be 0. C, change in enthalpy is greater than 0, change in entropy is greater than 0. D, change in enthalpy is 0, change in entropy is greater than 0. So I am giving the solution for this problem. Throttling process is an irreversible process during which enthalpy will remain constant. So I wrote here, throttling process is an irreversible process during which enthalpy will remain constant. Means we can say that throttling is a process in which there is no change in enthalpy, but it is irreversible process. So whenever the process is irreversible, the change in entropy will be positive, means greater than 0. So if we see the option, so option D will be correct, because in option D, change in enthalpy is 0, but change in entropy is greater than 0. So the correct answer for this problem is D.